Hi everyone, thanks for coming. My name's Noel. There's a few faces in here I've met and seen before. For those who don't know me, like I said, my name's Noel. Work for a company called 47 Degrees. We're one of the gold sponsors of this conference. We also made the Scala Days app. So 47 Degrees, mainly a company that deals in consulting and developing and training. So if that's something of interest, we have a booth here, and I think we've got about 7 guys as well. So we're all pretty friendly, so come and say hello. If that's not enough, we're also running a couple of competitions. So there's a chance to win some headphones, some Beats headphones, and also we run our own conference in October in southern Spain, which is a great time of year to go there. So there's a chance to win some tickets to that and an accommodation for the conference. Okay, so what I'm going to talk about today, I want to introduce what type classes are. Sometimes when I've spoken with people who are particularly new to Scala, they kind of don't understand them, and they're a little bit of a different concept from if you've come from, say, a more object-oriented, Java or C# background. There are some similarities, and the patterns do appear, which I'll show. But to complete newcomers, they're not always intuitive and not always what you expect. And well, I've done a few talks in the past, and I've always found them interesting, but they've always been maybe a little bit dry. It's here's how you use this library, or here's some nice ways to work with enterprise libraries in a functional way, and things like that. And maybe a little bit dry. So I thought while I'm explaining type classes, I'll do this hopefully in a more interesting way, and maybe introduce a new concept around what a genetic algorithm is and things like that. So and see how I got on with making the two things work. Okay, so here's what we're going to talk about today. We'll start with a pretty clear definition, hopefully, of what a type class is. We'll then take a bit of a sidestep and look at what a genetic algorithm is. And then we'll put the two together and hopefully make that work. Okay, so type class, what is a type class? Well, it's quite clear. It's ad hoc polymorphism, right? Well, no, right. We need a bit better definition than this, right? When you start looking around and trying to get definitions of what type classes are, this is a phrase you often come across. And I mean, it's correct, and it's quite clear what it means, but if you're not sure of this terminology, or it's a completely new domain, then it may be a little bit strange. Okay, so let's think, well, where can we start? Well, who in the room has maybe a Java background before Scala? Who's not? Okay, right, well, that's good, because we're going to start with Java, right? Okay, so if you cast your minds back to the dark days when you were Java programmers, you might remember there's a class called arrays. And it had a method called sort on it. It still does, actually. And for those not from the Java background, all this definition is saying is that we've got a general type T, and that we want to sort an array of T's. But in order to sort the array of T's, we need to know how to compare some T's. And that's it, right? So clearly we don't know what a T is, The compiler doesn't know. Nobody knows what the T is until we want to actually use this. But if we look at this comparator type, it's got one real method on it, and that's this compare. It takes a couple of T's and returns an int, okay? So you would imagine here, if the two T's are equal, then that integer is going to return 0. If one T is less than the other, it'd be negative, and vice versa, okay? So the nice thing is that we can create our own types, and then we can use that comparator to sort arrays of our type. So say, for instance, still in Java land, when we were writing POJOs, of course, we'd have had getters and setters and equals and toString and some constructors probably and all that fun. But let's keep it slightly sane. Okay, I just want to create a new type here. This, the compiler, Java, doesn't know anything about this type. We wrote this. And all it does is it holds an integer. So clearly, because this is not an integer, it doesn't know, Java doesn't know how to sort this. If you get two int holders, it doesn't know what sorting them means. Okay? But we can create our own comparator here. So again, we're still just writing plain old Java. We implement this comparator interface for our int holder. We grab the integers, we subtract one from the other. So now we can use this for our own type. Okay, we can now sort collections or arrays that contain our type. So here's an example, using the Scala REPL because it's quite handy for things like this. So we've got an array with a couple of these in, and as you'd expect, 50 is less than 100, so if we sorted this, we'd expect the order to change. Of course, the sort method is mutable, which makes me twitch, but we can then sort this using our comparator. And then when we inspect what's in our array, you can see now that's what's happened, is that these have been sorted. The sort method used our comparator to iterate over the values in the array and work out where the ordering should go. And so, I'm gonna, this is not a full type class definition, and we'll look at this in a bit more detail now, and maybe we'll see how this works in Scala. And what I'm going to show is a very similar example to what we've just looked at in Java land, but I've taken this straight from Martin's paper, which was introducing implicits into the language. So I'll send these slides around afterwards. I'll put them on Twitter, and they'll be as part of the video and things. And this links directly through to the paper. Okay, so in the paper we have this trait here called ord. Again, it's parameterized on this type T, and then we have a compare method. You might remember in the Java method, it returned an integer, this returns a Boolean. And you can debate on whether this is a good API or what, but that's kind of not why we're here. But the rule we can take from this is that this will compare two T's, and if A is less than B, it will return true, okay? Whatever that means for the type we want to use it for, okay? So we need to create an ord instance now for the specific type we want to be comparing with. So here's how we do it with integers. We just implement the ord interface, or the ord trait, sorry. It's a simple implementation as you'd expect. And now we can use this wherever we want. So say we wrote our own sort method, and we parameterize this, is that if we have a list of some type T, and as long as we can provide some kind of ordering for that type T, then we can use this method here. So this will take a list, sort it, and return us a new list in sorted order for whatever sorted means for that type T. And this would work as expected with what we've looked at here. We give an array, we give a list in reverse order, we pass our ordering, and it returns us one in the correct way. So what you can see, maybe this is like the Java one as well. This is a bit cumbersome, it's a bit ugly. We've got this backpack we've got to carry around with all our orderings in it to make sure that we want to order things correctly. And so it'd be quite nice if that just wasn't there. And so Scala gives us the ability to do this. And so we'll make a couple of tweaks to our implementation. And all we'll do here is make our int ord object implicit, and then we'll change our sort signature to have an implicit parameter for our ordering. And then what we're saying here for our sort method is at compilation time, we want to use this, but whatever we call sort with, the compiler must be able to find an implicit type for ordering of the type that we're looking for. And that's it. So in this case, we have an implicit int ord, so that's for ordering ints. And so if we call this for integers, we can see that this works. And this kind of works as you'd expect. This type parameter here, I didn't need to put this here because the compiler is smart enough to work out we're dealing with ints. I just wanted to be maybe a little bit clearer. And so the nice thing is that we have the ability to sort, but we don't need that full context in our faces for something as simple as this. And then the nice thing is that if there's no implicit in scope, say we wanted to sort with strings, does anyone have an idea what's going to happen here? Say again, sorry? Yeah, so what's going to happen if I try and do this, if there's no implicit for strings? I can't hear, sorry.
Compile
Yep, compile error, yep. So there's no magic here, there's no default action, there's nothing that will happen in place, there's no magic, nothing like that. Literally, we need to have an implicit there for the type in which we want to work with. And so let's just try and make this a bit more general, because what we've seen here is a type class. And so for a function which is parameterized for a certain type, if we have an implicit parameter which needs to use that implicit that type, that is generally what a type class is. And this might look a bit cumbersome and a bit strange, and maybe you kind of don't like this. But once you notice this, and once you realize that this is what a type class is that you start to see this pattern everywhere. And the way to think about this, and this is quite a nice way I like to work with type classes, is you think of this as enhancing the type, is that we've taken integers in our example here, and we've provided our own way to sort these by the rules that we've set. So what this is really saying is we can add our own interface onto other people's classes. You know, we didn't write the int type, but we've managed to sort it to the rules we want to. And then if we create our own brand new type, like I did with the int holder for Java, is that we can then provide ordering for that. We can use another library, which gives us our own types, and if we want ordering for types in that library, we can provide that here. And I think this is really quite powerful. This is not something you generally get with Java. I mean, I showed a way to do it, but it's not really the way things are done in the kind of object-oriented world, is that things tend to work with inheritance. So you would have to inherit, you'd have to extend, say, comparable or similar. And what that means is that that needs to be set at the compilation time of the original type. But now we've got this way to add our own implementations onto a given type. And then we can make this really, really comfortable by using the enhance my library techniques that come with Scala, where it looks like we've got our own methods on these types as well. And this is what libraries like cats and Scala Z did, is that it gives us these extra functionalities on given types that are not part of that type in the first place, but allows us to work with them in such a way. And it's really quite powerful. And so I'll just show another example. Well, I'll show some examples that you may be familiar with already. For those of you who play JSON, I mean, the reads type is a type class. So it allows us to do things like this. So we can extract some JSON, some part of a JSON, and then we can automatically convert this to a type. And that's our type. We wrote person. We have the ability to do this. And if we drill down into how this actually works, we come across a method that looks like this. And this is what I was just saying. This from JSON is parameterized on this type T. And then we need an implicit reads T. And then if we were to look at what that meant, is that we could go into the reads object, and when we need to implement our own reads implicit for our type person, we'll have to provide the rules that when we get some JSON, we're going to have to drill in and find all the fields that make it a person. And then there might be some rules for if the JSON is wrong and things like that. But all it gives us then is that the ability to use this from JSON, so go straight from JSON to any type. And as long as we've created the rules for how to get to that type, this will work. And it's a really nice separation. We've managed to keep the use of extracting the field into our object in the rules of how to do it as well. Okay.
One question, sorry.
Hi, yeah.
Doesn't that have to be a person because it's
Yeah, that's a typo. Sorry, yeah. So yeah, that's absolutely right. That reads should be reads person. Sorry about that, yeah. And then of course, there's the same thing works for writes as well. Okay, another example. If we look at, say, the type level cats library, the type level cats library makes a lot of use of type classes. And so now that we're all familiar with type classes, we might see some signatures like this. And hopefully this all makes sense now. No, it doesn't really, does it? But what I really wanted to show here was that if we want to use this method, or whatever this means, whatever these types mean, is that we just need to make sure that we have this semigroup type in scope for whatever we're doing here. And then you'll find that when you start to use these libraries a bit more, you start to understand what it means to work with a writer, which is effectively appending or writing to something. And semigroups give us the ability to generically append. So while we could have provided lots of ways to work with this, we want to append to strings, we want to append to files, we want to append to lists, we can just forget about that and say, if you want to append to something, just provide a semigroup for it. And then if someone finds this really funky way in the future of doing these really cool appends, it will work with this out of the box, no questions asked. Okay? So I have a bit of a proposal here, is that I believe that implementing a genetic algorithm is actually a really, really nice opportunity to use type classes. Okay, so like I said, we'll take a sidestep and we'll look at exactly what the definition of what a genetic algorithm is. Okay, so if we look from what Wikipedia says, it's a search heuristic that mimics the process of natural selection. Okay, so what we're really saying here is that we're gonna work with a population of something, and the fitter ones survive, and then we're going to kind of reproduce this population and see where we get us. Okay. Sorry, is that a question? No. Okay, so let's look at what we're going to do. We're going to randomly generate some stuff, work out which is the best, then use that best to generate some more stuff, and then we're just going to repeat that forever. So this is the classic monkeys on typewriters doing Shakespeare, isn't it? But okay, I mean, I'm being a bit silly, obviously, but we'll delve a bit deeper into this. So we need a way to kind of represent this stuff, what these things are. So I think a nice thing we could do is maybe have a binary string. And so I suggest here we use maybe a list of Booleans. So I've used a vector here because that's a bit easier for random access. If you're not comfortable with vectors, they have the same kind of interface as working with a list. Okay. And so just going back to my basic slide a minute ago, a few more steps of what this is going to do. So we're going to take a population of these chromosomes. We're going to measure each of these chromosomes against some kind of fitness function. And we'll look at what that means in a minute. And then clearly the fitter ones are the ones that are more successful running against this function. We're then going to take these chromosomes with their weighting and we're going to randomly select from them. But what we want to do is we want to say the ones that were fitter are going to have a higher chance of being selected. Okay? And then we're going to do some kind of mutation and reproduction within this pool to hopefully create even stronger ones. And then we might just kind of add a few strange mutations in just to see where that gets us as well. And that's our new population. And so that's effectively one iteration of this algorithm. Okay. So here's a proposal for what this algorithm will look like, this iterate function. We're going to need some kind of fitness function. Given a population, it returns us a new population, and that's it. So clearly the fitness function will depend on what our algorithm actually is representing, because we've been quite abstract so far about this. So what we need to do is we need a way to convert from this binary string, which is supposed to represent stuff in the real world, into actual real world stuff. So here's a way we could do that. We could create a little trait here, just with a single method on it, as A, which takes a single chromosome and is able to understand what that binary string is supposed to mean, and then create that type for us. And we'll look at some concrete examples in a little while, just to kind of hopefully make this a bit clearer. So we just need to change our iterate signature just ever so slightly. And so I'm going to add this new parameter on here. So we need our fitness function and our population again, but then we also need a way to convert from the chromosome to the real thing. And so we can have this implicit genetic type here, genetic parameter here. And hopefully you start to see now that this is actually a type class. We're using this in the way that type classes are here for. Okay. So now that we have our fitness function and we have the population, we can look to create a pool to pick our new population from. And so what we want to do is we want to randomly select from this population, giving a higher chance to the fitter chromosomes. So say we had a population that looked something like this. You can see here that one of these chromosomes was really, really fitter than the rest of them. And so when we randomly pick from here, we want to really have a higher chance of picking this orange one at the bottom. And so a possible implementation, or the definition of the implementation, could look something like this. This is often called a roulette wheel, maybe a dartboard and things like that. And so given a list of these chromosomes with their weightings, that effectively gives us a function. And that function is like our ability to randomly pick from the pool. So you can think of this as it would pick a number between 0 and 1, a double, and then that will pick a point on the chart of where we'd go from. So obviously this would be 0, this would be 0.25, half, 3/4, and then 0.99. So we can just look at the non-significant digits from a double. Okay, but being all diligent professional programmers that we are, we want to make sure that we're testing this properly, because what we're dealing with here is effectively this is a very random situation. We're dealing with random things that have been generated randomly, and we want to pick from this pool at random. And so the best thing to work with something random is to use even more randomness. Are people familiar with ScalaCheck? Are people not? Okay, I don't want to get too sidetracked by what ScalaCheck is, because I could speak about that for hours, and I often do. But a brief intro is ScalaCheck is a very different library to something like Specs or JUnit, in that you tend to provide rules or properties for your implementation that you are sure must hold at all times. So if we were, say, implementing an absolute function, we'd want to make sure that the property of our function is that it never returns a negative number or things like that. So what we would do is we would think of some properties, and then the library will provide random values for us to test that these properties always hold. So that's in a nutshell what it is. And I've got some code that looks at some ScalaCheck implementation in a bit, and hopefully don't get too bogged down on the details, but I just wanted to show that this is quite a nice, neat way to actually test this. We're using something random to also test something random. Okay, so one thing we need to think about is what's a property of this roulette wheel, this dartboard that we've seen that will always hold? Like something we can do. We could provide some kind of random set of a population and then work out what will always hold true for our population. Okay, so here's one idea, is that if our population has a single chromosome within it, that is so much fitter than the rest that it takes over half of that wheel, then the midpoint of the wheel will always return that chromosome. Okay, so if we imagine the midpoint is here, and so we would always select 0.5 on that function, you can see here that wherever we pick, if we give different implementations, is that as long as we have a chromosome that's always bigger than half of the population, we should always get that picked. And here's a way to test this. Okay, so we provide some chromosomes here that we don't care about, and then we also give them their weighting. And so ScalaCheck gives us all of that information just randomly. And then the nice thing here, sometimes these lists will be empty as well. And then also in the middle of this, we provide our own chromosome, and that's the one we're looking for. And what we do is we take the chromosomes the other chromosomes, and we find out the total of their weighting, and we add 1 to that. So that's bigger than the sum of both of them. And then that's the weighting we give to this chromosome here. And then this is just explaining what I said. And then when we look at this roulette wheel at the midpoint, it should return this midpoint here. Again, that's a bit of a whirlwind tour, especially if you're not familiar with ScalaCheck. But that's quite nice, because ScalaCheck will run this at least 100 times. And the nice thing is this then passes. So we get a nice level of confidence here that our implementation is actually quite a good one. Okay. And this is not all encompassing. This is not a test that proves that everything we've written works, but that's just one property. And the more properties we can think of, the better this will be. So what we've done here is that we had to provide a way to pass this double into our implementation. And what we'll have to do is in other tests, which maybe I haven't shown here, is that we want the ability to control this value that is passed so that when we look at other integration tests, we can pass in the values we want to make sure that this is getting returned as we would expect. So we want to just maybe, we want to maybe just change our implementation of our iterate function ever so slightly, and that we call this next double here. So now we can create we can generate streams of known doubles, and then when we test this, we know what numbers are going to be passed to that roulette wheel. So we can then determine what chromosome should always be picked, and that would make testing this a lot easier. But then, of course, for our real production live implementation, we can just give it a different function, say the next double, and that will just work especially, and then we don't really have to think about where these doubles are coming from. Okay? So this was creating our mutation pool. This is not our new population yet, but what we found are the really, really strong chromosomes, and the ones which were really strong have a higher chance of being picked, and they may be picked more than once as well, which is nice. So now we need to effectively marry or mate or use these chromosomes together to create our new population. So how this works is we take a chromosome from the pool, and then we take another one from the original population, and we line them up side by side, and at some arbitrary points, we flip the bits round. So we get part of the fit chromosome, and then part of another one, and that gives us a brand new chromosome. And then that might be fitter, or it might be not, but we'll see where that takes us. And so we take a couple of chromosomes, we pick an arbitrary point, we flip the bits, and then we just throw the original one away. And this is our new chromosome then. And then again, we can test this with ScalaCheck as well. And so one property of this is that if we provide two fragments of a chromosome, we can put them together and pass that to our crossover method, and we can tell the function where the crossover happens, and then we know what we'll return because we've given it all the information and we knew that up front. So this is a slightly more involved test, but basically here's our crossover point that we take from ScalaCheck, and that just gives us the full length of the chromosome. And then here we pass in effectively full chromosomes that have been split. We stick them together. We then call crossover, and then we know the expectation will be the left of the first chromosome and the right of the second chromosome. And again, this works quite nicely. And again, just as an aside, because now we're relying on this integer to pass where the crossover point happens, because we want to be explicit about that in our tests so that we know where it actually happened. So that just means we need to add this unit to integer function to our iterate signature so that we can use that in our tests, but then also we could use, say, the random functions we get with the Scala utils. And then finally, we get some random mutations. So what happens here is that if our algorithm is iterating towards a point where it looks like we're quite strong, this might be a local maximum, and there might be an even stronger point somewhere else in our solution space. And so if our population is, for some reason, quite biased towards a particular solution, we might be missing out. And so we'll just throw in some random bit flips or mutations, and that might take us away and maybe put us closer to an even more successful goal. And so we'll just simply randomly select a few bits to flip. And so we pick 3 here, and we flip them around, and this is our new chromosome. And then another thing to mention here is that maybe we don't always want to do this. So sometimes we'll mutate, sometimes we won't. And I won't show a test for that, but that should be quite straightforward to test. And we're done, and we ship it. And so our final iteration signature looks something like this. So we have our fitness function for the type we want to work with. We have some way to control the randomness when we want to. And then basically, given a population, we get a new population as long as we know how to convert from a binary string into what we're actually dealing with. So really, what I want to say here is, as long as we have a type class for that binary string, we can use this algorithm, and this should work for any implementation. Okay, so that's all the kind of boring, dry stuff. Thought we'd have a quick look at this algorithm in action. Okay, so one thing we could do is maybe find the optimal solution to a function. And I mean, clearly we know where the optimal solution is for this, but but we could maybe plug this into our genetic algorithm. You know, if we know the function of this graph, which is quite simple to calculate, we can then provide that as a fitness function and then work with some numbers. So the graph is our fitness function, and all we need is a way to convert from a binary string to a number. And that's relatively straightforward. So we need our implicit implementation for the genetic type class for integers, and then we need to provide our implementation here. So given a chromosome, how do we make that to an integer? And we simply spin through all the bits, and we shift right with each iteration. And then if it turns out that the bit at that point was true, we add 1. And then we'll find that that gives us a number for a given chromosome. And then we can look at how this does. So here's an example. So this is running for 1,000 iterations. And we can see here that at the start, because the numbers are all over the place, the binary strings are all over the place, that it really is quite random. And then at some point during the iteration, one or a few of the binary strings were very close to the target we were looking for. And then we get very, very close here. And actually, if we zoom in, we can see here that it's not just sitting on the number of the target we were looking for, because there's still inherent randomness, and we might find mutations and things like that maybe take us away slightly and then bring us back to the number. And then maybe just another one, and this is a similar number, just another run, and actually this found the target maybe a little bit quicker. And so I did this with a population size of 30. So there were 30 chromosomes in each iteration, and I did this for 1,000 iterations of the algorithm. And then maybe a slightly more interesting one to finish off with is maybe we could do some modern art. And so, like I said, we're really at the mercy of our imaginations here, in that as long as we can provide a genetic type class for any type, then we can use our algorithm, which is really, really quite cool. So how about creating one for this type? Okay, and then here's the idea. So we'll use this binary string to create 50 triangles on a canvas. So each triangle will have 3 sets of XY coordinates, and it will also have a color. And so what we need to do, assuming a picture of this size, we need 60 bits per triangle for 50 triangles, 24 bits to say what the color is, and we'll throw in one more color just to give the canvas a background color. And so for this implementation, we would need a binary string of just over 4,000 bits. Okay? And so, well, what's our fitness function? When we looked at this graph a minute ago, it was quite clear that if we had a number, like, it's quite easy to put it into the graph and see how close we are. And we were looking at, all we wanted to do was get the highest y value possible in our previous iteration of this. But now, what does it mean for one picture to be fitter than another? Well, we can just compare this to an image that already exists and say, as we get a bit closer, we can maybe see just how close we get. Okay, so our fitness function is basically going to just compare some images. Okay, so given both images, for each pixel, compare the RGB values, subtract one from the other. Do this for all the pixels and then get the sum. The smaller the total, the closer we are to our target. Now, I know that this is not the best image comparison algorithm ever written. And, we could probably have a whole conference on image comparison algorithms. But hopefully, we'll see, hopefully this will work for now. But clearly, this is not the most efficient. So there's one more problem we need to overcome. It's a not very big problem, really. But our fitness function for our algorithm was A, too long. But now we want to use this with 2 images. So we can't really change our algorithm to accommodate this, because it would break other implementations of the algorithm. But of course, this is pretty simple. We can just provide a curried function. So our fitness function would look something like this, and then the Mona Lisa or whatever would be the first parameter, and that gives us a new function of buffered image to long. And then we can provide our iterated values with that to give us to give us hopefully a value. And so let's have a look. Let's have a look at how this went. Okay, so there we go. No, so that was 1,000 iterations. Okay, and so this is 2. You can see, look, the background's changed. And let's get I know the picture isn't great on the screen, but it's got a little bit darker. And look, the triangles are getting out to the corner. And that's 5,700 iterations. Yeah, and that took me 3 days of running that. So I'm pulling my hair out, because this was just before I went to New York to give this talk. And I was like, oh no. But I think what this goes to show is that, if you have other ways to get solutions, then genetic algorithms are not always the most efficient. If you don't know your solution space, then genetic algorithms can be really quite fruitful. And I think people like NASA use this for creating, say, antenna configurations for work out the best way and things like that. So there's some quite interesting images of these like really bendy wires and things that apparently are very good at receiving signals. But what has been nice here is that the type classes provided this really neat interface into our algorithm. Both of the things I showed there used the exact same algorithm, but all we did was change the fitness function and provided a way to convert from the binary string into our representation. Okay? And another little side effect of this project has been, although we're dealing in an inherently random situation, using another random tool works quite well as long as you have control. And it shows that you can be deterministic in what really is a kind of non-deterministic setting. And so, what else could we have done here? So, what are some other suggestions? Maybe you can think of your own. So here's one I thought of. We could write a genetic algorithm and provide a fitness function of maybe a set of unit tests, and then let it randomly generate an AST and maybe write us out of a job. Or racing cars. This is quite cool, actually. Does this work? So this is done in JavaScript, and these are all randomly generated. And then this will crash in a minute, and then it starts again because it knows this was the fittest because it went further along. Is it ever going to stop? Oh. Give it a sec. There we go. And so that's died there. And now these are more closely related to that one and things. And if you leave this for a couple of hours, it gets quite good. So I need to close that. Or maybe, I don't know, maybe a kind of poker bot or Counter-Strike bot or something. I don't know. Maybe you can think of your own. It's been quite a little interesting experiment. That's basically all I had time to talk about. I'll leave up some links here, and these are all clickable through the slides. So this top one was kind of the inspiration for the talk, really. As this fella who did iterations of the Mona Lisa, and he did it in C#. Technically, it wasn't a genetic algorithm, and all he was doing was kind of iterating on random bits and not really having the kind of mutations and crossover and things. But he did really well, much better than I did, actually. This book here is kind of the de facto Bible for dealing with genetic algorithms. I think it was written in the 80s, and then I also put up a link to my talk. That's all I really had. If you have any questions, I'd love to hear them, and I hope you enjoyed it, and I hope you learned something as well. So, thank you very much.